So this completely define my UFC provided these F matrices are unitary. And so this was solution of the Pentagon's equations. And it's unitary if F are unitaries. And we have seen that if we want braiding, we need the R symbols. And it gives a UMTC if we have this non-degenerate braiding, which means that the determinant of the S matrix is different from 0. Okay, so that's basically the summary of these 2 lectures. And then I told you that there were some important quantities in the game, which are called the modular data. And what are the modular data? They are the S and T matrices. Okay, and for a long time, people thought that if I give you the S matrix, which again describe the mutual braiding of my anyons, and the T matrix, which describe my twist of my anyons, it was sufficient to fully determine the UMTC. Okay, so in other words, if I give you the S and the T, and this extra condition of non-degenerate braiding, that I could completely determine the F and the R symbols, in other words. So they were fixed by this data, this modular data. So this is actually not true. And the first counterexample was given in the 2017 by Mignar and Schauerberg, who found a counterexample where you have the same fusion rules, the same S matrix, the same T matrix, but still different F and R symbols. Okay, so I think it's important to keep in mind that in many cases, people may only give you the S and T matrices, which are somehow way more simpler to compute than deriving F and Rs, although they can be written in terms of those symbols, but they are also other algebraic structure that allows you to compute them in a different way. If some of you are interested, you can have a look at this very nice paper by Eric Rowell and Dengong Wang from 2009. Where they classify all UMTC. So it was really the beginning of this classification business of UMTC. Classification of UMTC of rank lower or equal to 4. Okay. And here they really classify all UMTC. So they also give you all the F and all the R symbols for all categories, all unitary modular tensor categories, so all anyon theory with less than 4 species of anyon. That's very cool. Yes, that's the number of objects. Yes, the rank is number of objects. And they found 35 different UMTC. Okay, so that's already a very good starting point, because suppose you have your favorite Hamiltonian or microscopic model, and you have a way, for instance, to compute the ground state degeneracy on a torus or any genus surface. You find a given number. Let's say you find 3 on torus or 4, and you want to identify your UMTC. It will be definitely part of this catalog. Okay, and then in 2023, people tried to go slightly beyond. So I think it's Orwell and when. So they pushed this classification down to rank lower or equal than 12. Okay. But in this paper, they were not able to compute the solutions of pentagons and hexagons, but they provide the modular data. So this paper, they give all modular data for UMTCs. So they give you all the S and T matrices which are compatible with the modular structure of this tensor category, provided the rank is lower or equal to 12. And they found 609 solutions. But of course, as I told you, giving S and T is not sufficient. So it might well be that if you would be able to solve pentagons and hexagons for these 609 solutions, you will find a way more, a larger number of solutions and different Anyon theory. Okay, so that's the current state of the art. So this paper is still unpublished. They are updated it almost every 2 years or something like that. But the latest version, I think, from 2025 available on the archive. This is the last result that which is known. Okay.
Question online?
Yeah.
So is there an understanding of how the number of solutions grows as the rank?
No, well, I don't know the answer. I think it's a very, very complicated problem. And especially if you look at the solutions, how the number of solutions varies with the rank, it's a completely oscillating number. So they give the table for rank 3, rank 4, blah, 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 up to rank 12. And you can see that the number of solutions for rank, I don't know, rank 10 might be lower than the number of solutions for rank 7 or something like that. Okay. So what is clear is that if n is a prime number, okay, you will certainly have less solution than if it's not a prime number. Because if it's not a prime number, you can also build solution by combining UMTC of lower rank.
Oh.
Okay, so if you have,
so
for
instance, is there a notion of an irreducible UMTC in the sense that you something like a simple group or some is there a notion like that?
Yes, yes, exactly. So some of them can be built out of simple groups, as you were saying. And of course, if you have a, let's say, a rank n category, a rank n UMTC and a rank n prime UMTC, you can do an operation which is called stacking. So if you have C, which has a rank n, and C prime, which has a rank n prime, you can do the stacking of both. Usually it's, well, depending on literature, it's written like this. And then you have a category of rank n plus n prime, or n times n prime, sorry. Okay, so that's why if the rank, your final rank is a prime number, it cannot be decomposed in that way. So you have more solution when the rank is not a prime number. Yes.
Yeah, thank you. Thank you.
Sorry, knowing these two rank here. So you can, if you have a rank n category and another rank n prime category, you can stack them and the final rank will, so there is an operation that allows you to build a rank n times n prime category. Yes, yes. In this very specific case, yes. Does this answer your question? Okay, yes, yes. Okay, and finally, there is another, so that's the current state of the art. So again, we don't know whether this 609 set of modular data give rise to only 609 UMTC. some of them may give rise to other solutions, and that's still something which has to be investigated. So there is also an extra ingredient that I haven't discussed so far. So the reason for which the M of UMTC means modular, okay, it's because these S and T matrices obey some very specific relation which stems from the projective representation of the modular group. Actually, they are projective representation of the modular group. And one property also which can be extracted out of that is a so-called chiral central charge. So experts in CFT knows that certainly better than I. Which in this context of unitary modular tensor category is only defined modulo 8. So I will give you the expression of that and will tell you what it means physically. But in this precise context, sometimes it's called also the topological central charge. So you will see both in the literature. So it's denoted C, okay? And it is defined as follows. So we have E2I by C over 8. That's where the mod 8 comes from. And it is given by this combination, sum over A of dA squared theta A. It's a 2 yes, sorry, 2I by yes. Okay. So this central charge has several physical meaning. And one should distinguish two sets of UMTC, or two sets of topological phase, or two sets of Anyon theory. The one for which C equals 0. Okay, these are called achiral phases. And C different from 0, obviously, chiral phases. And physically, this chiral central charge can be related to some physical quantities. So if you want to know exactly where it comes from, have a look at the ICTS paper from 2006. It will give you exactly the dictionary, but basically, if you compute the specific heat, okay, it's directly proportional to the central charge up to some factor. Yeah. So it does thermal current on the boundaries. Yes. Yeah. Okay.
Is it true for fermionic topological order case also?
Sorry?
This equation.
Yes.
Is it true for only bosonic topological order, or?
So this is for both. So okay. So that's an extra distinction that I haven't done. Everything I've described here, and especially this non-degenerate braiding, it only holds for bosonic topological order, what is called bosonic topological order, which essentially means that I have a unique vacuum. Yes. Fermionic topological order is something more involved. So some simple examples of Carroll's theory of the well-known, of course, fractional quantum Hall state, where you explicitly break time reversal symmetry with a magnetic field. So the theory will be like Carroll. And now for in condensed matter, for microscopic models, the most famous one, like again, string nets or ICTS quantum double. the emerging theory, so the proper Anyon theory, which describe the excitation of these models, they all have the property that C equals 0. Okay, and actually you can prove that if you have a Hamiltonian which are local commuting projector Hamiltonians, and that's exactly what you have, for instance, in the toric code. They always have a vanishing central charge. Okay. Yes. Sorry? Finiteness of what? Yes, in this case, yes. No, here I only consider semi-simple categories, otherwise it's not. Yes. Yeah. So you want to know what, well, here you know that if, well, you can see that if I take C or C plus 8, I have the same C. That's all I can tell. Now, physically, the reason for that is a bit tricky. It's related to the fact that well, there are several ways of understanding that, but you have this E8 category, which is essentially based on the vacuum, which is a Carroll theory, and you can always stack any UMTC with E8, and then you will change the central charge by 8. Okay, I don't know if it's really enlightening, but yeah, it is. Yeah. Anomaly. Yeah. Yeah, I don't know the precise dictionary because, let's say it like that. All UMTC can be described by some TQFTs, okay, as well, but it doesn't work the other way around. So it might be slightly more general in the TQFT framework. Yes.
Is there any simple way to see why this chiral central charge is related to this modularity matrix?
I don't know. To be honest, I don't know how to simply answer that that question. Maybe Frank has. Beschietikin, yes. So again. So again, it depends on which theory you're discussing. When you have, when your TQFT can be described by a UMTC, that's exactly the same central charge as the one you would get from those TFTs. But this is, yeah. So Tureyev-Viro is exactly for A-Carroll phases. It can be A-Carroll. Yes. Yeah. So that's why in this case it's not described by a UMTC. Yeah. Yes. No, you can have A-Carroll phases, which comes out from other sort of Hamiltonian. But what you can prove is that if your Hamiltonian is built on some of local commuting projector, then at the end of the day, you will deal with a Carroll central charge, which is 0. Yes. And one important thing also to keep in mind is that all these A-Carroll phases, so A-Carroll UMTCs, they are actually described by what we call by what we call Drinfeld centers. of some category, some UFC, or let's say, even some FC, not maybe UFC, but. So the Drinfeld center is it's not just something, because there will be a lot to say about it, but let's say that if you take any category, any fusion category, you can build what we call the Drinfeld center. So you start from a category C, okay? And you can build the Drinfeld center, usually called Z of C, of this category. This is a UMTC, even if C is not a UMTC, okay? And it's a UMTC with a zero central charge. And that's exactly actually what you do when you're playing with string nets or with KIT-AF quantum double, because if some of you are familiar with string net, maybe someone will explain string nets at some point, but well, I could do it, but it will take a little bit of time. So with string nets, usually you have your microscopic degrees of freedom. Okay, which are given by some categories, some groups, some representation of groups, some quantum groups, some whatever you wish. It's given by your fusion category C. Okay, so these are your input data. Okay, so it's usually what we call the input category. Okay, and the whole machinery of the Levin-Wen construction takes you from C, and the eigenstate and the excitations of your string net Hamiltonian, they are described precisely by the Drinfeld center of C. And the beauty of this string net construction is that you can really do it for any input fusion category. Okay, there is well, in the first version of the Levin-Wen paper, we could only use some of them, but then it has been generalized, so it's called the generalized string net. And so now for any input category, so you can define your degrees of freedom microscopically. You give me the fusion rules and the F symbols. Basically, that's all you need at the microscopic level. And at the end of the day, your spectrum will be described by the excitation corresponding to the Anyon of the Drinfeld center of this category. And again, since it's a Drinfeld center, it has a vanishing central charge, and it's a chiral phase. So all string nets can only describe achiral phases. And the nice thing is that because now we can do it for any input category, we can build all possible achiral phases out of this Drinfeld center construction. Okay, so this also answers Frank's question that we had yesterday. So we have a toolbox. We have a Hamiltonian, which gives us all possible achiral phases, but we don't have the similar thing for chiral phases. And that's certainly one of the most challenging questions in the future. Yes. Yes. Most of them are not Drinfeld center. Yes. Yeah. Many of them have non-trivial central charge. Yeah. Well, let's say that in the classification, chiral phases are more common than achiral phases. But for us, when we want to do some actual calculation in the lab, if we stick to exactly solvable model, usually it means that it has this LCPH structure, local commuting projector Hamiltonian structure. And then we always deal with chiral phases, which are, from some respect, a way simpler. And especially for, if you want to do some variational calculation, like using tensor network or stuff, actually, it's pretty fair to say that we only know how to implement achiral phases, and we still don't know exactly how to describe a chiral phases of material. Yes, in most cases, yes. yes. You can think about it. The short answer is yes. There are a couple of subtleties, but basically the answer is yes. There's a one-to-one correspondence.
Question online?
No, I don't think. No, I don't think so, because you know that there is this Morita equivalence. So if I just give you the Drinfeld center, the inverse tube algebra. Yeah, well, no, but it depends what you mean by constructing them. You give me all the data of the Drinfeld. Well, again, as Frank said, so if you know it's the Drinfeld center of a given category, how can you identify this original category? I'm not sure it's completely straightforward. If I don't tell you anything on it, no, it is not unique. In general, it is not unique. There are several inputs which leads to the same Drinfeld center. This is called the Morita equivalent category. So maybe I can just find that. So what is Morita equivalence? So we will say that C and C prime are Morita equivalent if Z of C equal in some sense, because again there are some equivalence of C and C prime. Okay. So indeed, for a given Drinfeld center, we may have different original category, for which the center is identical, is the same. Yes. Not sure. Could you say it? You want to know what is a Drinfeld center of a Drinfeld center? Yes, we can do it. It will be a different category. And it's pretty simple to build, actually, because the Drinfeld center, okay, so Z of C is a UMTC, okay? And if you want to take the Drinfeld center of a UMTC, okay, it's always two copies of the Drinfeld center with opposite chiralities, okay? So let's say that Z of C will be built like the stacking of Z of C cross Z of C with opposite chirality, but they are a chiral in this case. So it will just be a stacking of two identical Drinfeld sets. And this holds actually for any category. So if in general C is a UMTC, okay, so more generally, if C is a UMTC, Z of C will be equal to C cross C bar. Even for non-UMTC, even just for fusion categories, for any fusion category, even if it's non-braided, even if it's non-whatever. Yeah. Is a time reversal conjugate. It's just two copies with opposite chiralities. Okay, so there was a question online.
Yeah, so my question is, can you elaborate on the meaning of the word tensor in this UMTC?
The meaning of this box here?
No. In the title UMTC.
Why is it a UMTC?
Yeah, exactly.
Okay. Yes, so fusion category are specific example of tensor category. Okay, so we could have.
Oh, I see. Okay.
Okay, so it just, yeah. So I think we start from tensor category. And tensor category essentially means that we have only fusion rules. Okay, we can do the tensor product of objects. And then if we add the condition that the fusion rule, if we have the F symbols on top of that, so if you have some solutions, then it becomes a fusion category.
Mm-hmm.
If these fusion matrices are unitary, it becomes a unitary fusion category.
Okay.
And the rest of the story is over there. But it's also true that the T which comes out here actually should come from a parent of the UFC, which is a tensor category in general.
Oh, thank you.
No, this is true. No, these are some extra structure that you need to build the fusion category. But I just mean that unitary fusion category is just a specific set of tensor category in general. Yes, I think so, yeah. Yeah. They have to be monoidal, rigid, and semi-simple. Basically all the needs. But, okay. Yeah. The box. I can give you a simple example if you wish. So let's take, for instance, a Fibonacci. Fibonacci UMTC. Okay, so we have two objects. One, they obey fusion rules like O cross one. And I have the F and R symbols. Okay, I can find a consistent set of F and R's such that it's really a UMTC. Okay, and now I want to build a Drinfeld center. So this is my category C, and I want to build a Drinfeld center Z of C. So what I claim is that, so what is the meaning of this stacking C cross C bar? This means that my object, for instance, if we just stick to the object, so the object of C should be thought of as pairs like A, B, where A belongs to C and B belongs to the time reversal of C. Okay, so there are two possible. So this is a chiral UMTC. So it has a non-vanishing chiral central charge. So I take one object with a chiral central charge C, the other one with C prime, and all objects of my Drinfeld centers are just like pairs of objects. Okay. So now you may ask, how do I fuse that? So I have my four objects. So I have one, so I should put a bar, but I just remove it here. I have one toe, one, toe. These are my four objects in my Drinfeld center. And if I want to fuse, for instance, toe with one toe, so what do I get? Toe cross one. So I have to fuse them piece by piece, okay? So this gives me toe plus toe one plus toe two. Okay. And the same kind of thing holds for everything else. Is that clear? So basically, I look at all possible fusion of this and that, not this and that, completely separately. So it's like we Yes, yes. But in this case, it cannot be built with such a simple construction. It's not just a stacking of C and C prime because they are not UMTC. So this construction only works when it's when your initial category is a UMTC. If not, so for instance, if you take simplest example that Benoit will certainly discuss this afternoon, you take as an input category, you know, like, what shall we take? We take a group. We take like a S3, okay, which has 6 elements. This is a category. You can build a Drinfeld set. So usually it's called, okay, for a group, it's called VEC S3. So this is really the category built out of the element of the group S3. And in this case, the Drinfeld center of C, there is a construction that allows you to build it. This is known as the tube algebra. That's exactly what we slightly explain that. And this gives you the Drinfeld center. So all I said previously is that when the initial category is a UMTC, this tube algebra is sort of trivial, and you can directly write down the Drinfeld center. But this is not the case for an arbitrary category. Yeah. But it's non-trivial. It's completely non-trivial. So for instance, you may think, okay, so here we have 6 objects. Okay, so if it would have been a simple stacking of these 2 things, you would expect 6 times 6, so 36 objects into Drinfeld centers. Okay, but actually there are only 8 of them. Okay, so the construction is a bit non-trivial, but we can. And what Benoit is saying is that when C is a group, indeed, that's exactly what you have to do. So if C corresponds to a given vec G, okay, so the category made of the element of a group, then the Drinfeld center, Z of C, is also known as a quantum double of the group. And that's where the name Kitaev quantum double model comes from. It's enlightening. Double of C. This is exactly the same. Okay. But when you don't have a group, it's known as a Drinfeld center in a more general context. Okay. So this just means that if you have a initial chiral category, okay, so which has a central charge C, which is non-zero, okay. The other category that you have to take into account is a category that you obtain by taking the time reversal symmetric, the time reversal category out of that. So the one with the opposite central charge. Yeah, you have to reverse all associated quantities like F and R's and all that to have the full set of data which is consistent. So S and T matrices in the. Yeah. Okay. That's something else. I think the answer strongly depends on what you want to do. But let's say that when I wrote something like this kind of picture of representation, okay, A and B fusing to C, this will describe a 2 Anyon state. Okay, so really a state in a quantum mechanical way, a 2 Anyon state in which I have to specify what is A, what is B, and what is C. Okay. So you can really think about this as a cat, okay, where I specify A, B, and the way they fuse together in the channel C. Okay, but of course, if I have more Anyon, I will live in another different, well, like a many-body state. I mean, you have a... You just decompose it in the reps. Yeah, that's exactly what you would do. So if you take two spin half, you have to say whether you have a triplet or a singlet. And yeah, exactly. This is given by the fusion rules. But this depends on your Anyon theory precisely. So if I tell you the rule of the game are given by the object and the fusion rules, then you know exactly how many such states do you have, how many different ABC describe your Hilbert space. Okay. And then if you want to think about it in terms of operator now acting on those states, then it depends what kind of thing you want to measure. But then, for instance, in the pictorial representation that I have drawn previously, so suppose I have an Anyon A here, and I want to make such a process, okay? A with B. It means I have an operator which acts like a loop around my Anyon A. And so I can really interpret it in terms of a Wilson loop, of a measure of my object A with another object B, and there is a recipe which gives me the action of this operator. So I can think about this kind of drawing as an operator acting on a state A, and it will give me a result proportional to A or to the one Anyon basis in this case. So for instance, again, if you come back to your favorite toric code, for instance, you can always have such a process. So you have somehow a E excitation somewhere, okay? And you can make a braiding process with an M, and you can really make it in this. You have your Hilbert space, which is perfectly well defined. You have two objects, and you have an operator which does this process, which acts onto this set of states. No. The fusion is not an operation. It's just one data which tells you how you must describe your state. It's not a fusion process. It's not an operator acting on a set of states. Okay. Yeah. Actually, the Frobenius-Schur indicator is given by some R symbols. So it's part of it. It's part of it. No, it's in the F symbols. It's already at the F level, yes. Yeah, it's one of the F which gives the Frobenius-Schur indicator. But there is also, it depends which Frobenius-Schur indicator you're discussing. There's a Z2 and the Z3 Frobenius-Schur, which might also distinguish between different theories. But the one you may have in mind for semyon, for instance, is given by F symbols, yes. Okay. Yeah. Yes. Yes. You have a different pentagon equation to solve, and you must solve all of them. No. It's just another set of matrices, and you have to compute all its entries as well. So solving pentagons is really painful. Yeah. So for each entry of your pentagons, like if you start from something like this, 1, 2, 3, 4. So I have A, B, C, D. I have to fix E, F, G, for instance. That's certainly not the notation I had. But for each of them, you will have a set of pentagons equations to solve. I'm fixing everything. On the left side of my, on the leftmost side of my pentagons, I'm fixing all indices. There is no specific symmetries between these. Well, there are a lot of identity between the F symbols, depending on many things I could discuss, like reflection symmetry, time reversal symmetry, if it's symmetric. And if you have the vacuum somewhere, also you have simplifications in your pentagons. But let's say in general, for each set of indices, you have usually 6 indices for your F symbols, okay? And you have to solve all of them simultaneously. So all of them have to be compatible. Yeah, there are theories like that, yes, of course. Especially if you take the vacuum as E, for all anyons, you have always its dual, and if you fuse it with its dual, it's either 1, maybe plus something. Yeah. But the beauty of this UMTC business is that the higher you go in the rank, the more non-trivial example and things like that you can observe. So that's why. So it's still a field with ongoing developments, but some conclusion that might have been drawn on the example we had in hand with lower rank category turns out to be wrong when we found counter example with higher rank categories. So there's still certainly a lot of things to discover. Yeah. Okay, so everything I've said so far concerns what we call bosonic everything. Yesterday and today, bosonic topological quantum model. Okay. And essentially, it means that if you think about this Anyon theory as emerging from a given microscopic theory, it means that your microscopic degrees of freedom are essentially bosonic. Okay, so that's definitely not the case for fractional quantum Hall state, for instance, where you start from a given gas of electrons. But there are bosonic versions of fractional quantum Hall state. But now if you want to go to fermionic topological quantum order, it's not described by UMTC. It's a different framework. So it will be, well, usually you need to use what we call this SVEC category. You will always see that has to be superimposed. And I cannot really tell you way more with simple words for the moment. That's something I'm also learning currently, but it's a different framework. No, it's not completely different. That's one possible way of doing it, but I think there are also more subtle way of getting a fermionic topological order. That's not the only way. You can always... Yeah, you get modified pentagons, modified hexagons. Yes, yeah, okay. Yeah, and at the end of the day, you have this parity fermionic issue. Yeah, you have to take into account the fermion parity, which is definitely an ingredient which is not in the game. Yes, Sanjay. Well, my understanding of that is that the quantum double of a group is nothing but the Drinfeld center of the group of vec G. Yes. Maybe Benoit, you know a bit more about that. Yeah, it's a quasi-triangular half. Yeah. Yeah. But the thing is that this is a very specific example of Drinfeld center in the sense that you really start from vec G, right? Everything I tried to explain is somehow more general in the sense that it holds for any input category, even if it has nothing to do with a group from the very beginning. Okay, and yeah, with anything you wish, yeah. Any other question?
A question online? Yeah. So where did you use the fact that you have some bosonic structure or whatever in this discussion that you had so far?
Sorry, why? You're talking about this bosonic thing or?
No, you call this bosonic topological order or bosonic. So where in the construction is this statement that it is bosonic coming in?
You don't see it precisely. That's what I that's what I tried to explain. The thing is that the word bosonic here is just here to remind you that your microscopic degrees of freedom that you never discuss in everything I did here are bosonic. Okay, and you will get a unique vacuum out of that. So the only constraint is that if I have a physical system made of bosonic degrees of freedom, okay, if there is a topological phase built out of these bosonic degrees of freedom, it will be described by a UMTC.
No, my question is where in the construction, where in the construction did you use that they're bosons?
So I don't use it. What I claim is that if it starts from a bosonic microscopic thing, it will be described by that. But everything I've written here, I don't really take it into account. These are just some constraints that I put in my model, except the fact that I want to have a unique non-degenerate vacuum. No, but again. Yeah, sure. No, sure. I fully agree. But here, in this framework, I don't have to remind that my microscopic degrees of freedom are bosonic. That's all I claim.
No, but should there be a set of anyons that will fuse to give me a boson? Is that a necessary condition for this to happen? So can I, using the anyons...
That's obviously the case for the vacuum. So
for the vacuum, I see.
I always have my vacuum, and the extra condition for it to be a bosonic topological order is that there is a unique vacuum.
Okay, got it. Yeah, okay. Thank you. Yeah. Thank you.
Yeah, yeah, you're right. Yeah, absolutely. Okay, everybody's hungry or angry? Yeah. This can hardly be explained with simple words. Yeah, so it's related to the fact that when your central charge is non-vanishing, you have chiral edge modes, precisely. Is this what you're asking? And when you have chiral edge modes, you have a non-vanishing specific heat at the edge. Yes. So this chiral central charge also take into account the chirality of the edge modes. And it also means that when you have a system which is described by a Drinfeld center, so you have vanishing central charge, your edge modes will be gapped. So there won't be any gapless edge modes. Yes. Yeah, I only consider topological excitations, yes. No, it's not that they will not be in this theory, but you can have examples, for instance, where you have a sort of mixture between both. And this description only gives you the property of the topological part of the excitation. But they might be coupled to other degrees of freedom, and then you will also have to worry about it. Yeah. It's the same, yes. You cannot. Or maybe you can try to compute the T matrix. The twist, okay, so it's not only the information about the ground state, but you can, you know, this then twist business, and then you can have access to the T matrix, and the T matrix will be different for torical and double semi. As well as the S matrix, by the way. Yeah, but it depends what are the only information you have. So if you just have the ground state degeneracy, you cannot distinguish between them. Non-orientable. I don't think so. I don't think so, but maybe. I'm not familiar enough with non-orientable manifolds. I know one or two references. I could give it to you, but I'm not sure that even if you put it on the Klein-Botter or something like that, I'm not sure you can distinguish between these two theories. But definitely the ground state degeneracy, it's one information, but it's a very partial information about the theory. Not sufficient, yeah. No, it's not sufficient. Because again, if you look at the expression of the ground state degeneracy, I think it's a sum over all anyons of quantum dimension divided by total quantum dimension to the power 2 minus 2g. Okay, so it only depends on the quantum dimensions of the object. So it only depends on the fusion rules. But again, for the same fusion rule, you can have different FNRs. As to the ground state itself, can we reconstruct the whole data of the UMTC out of the ground state? I think you can certainly, so suppose you're on a torus, you can certainly extract the S and T matrices. And once you have these S and T matrices, you have a lot of information about F and Rs. But as I explained previously, you don't have all of them. There might still be some ambiguities. Oh, so these are these then twist things. So if you're on a torus, there are some operations that you can do. I mean, it depends what you mean. How do you do it? If you want to do it in a computer, for instance, you have to do some operation which connects some ground state to the other, compute the overlap by twisting your torus and changing somehow the boundary condition. And then you can really rebuild the T matrix and the S matrix. But once you have this modular data, S and T's, you don't have the entire information. In most cases, it's sufficient, but again, there are some counterexamples. So it's not completely general. No, I think that if you have all the ground state, suppose you're on a torus, if you have all the ground states of your ground state manifold, you can extract the S and T matrices. No, not FNR. That's exactly what you can extract S and T's. You cannot. You cannot.
Suppose I look at the Morse-Seiberg formula for calculating the degeneracies in each topological, Anyon sector. So for a given UMTC, I calculate these degeneracies. So and look at one Anyon. So is it that I can find a different UMTC for which this would be the ground state degeneracy?
Yes. Yes. Yeah, you have different UMTC which have the same ground state, like any abelian UMTC.
Sorry, maybe I was. So I'm looking at the degeneracies of each topological, each Anyon sector.
Okay.
So suppose I look at the 4 Anyon sector. Now I'm asking your question is that I want to find a UMTC for which this degeneracy is the ground state degeneracy for that UMTC.
Ah. I'm not sure there is a algorithmic construction for that. Yeah, maybe by coincidence for some fusion rules, maybe it will turn out to be true, but in general, but maybe no. I think no. I think the answer is yes, actually, Subhro, because if you think about a torus, the ground state degeneracy is just given by the number of objects. So you just ask me if any integer number can be interpreted as a number. I think the answer is yes. Yeah. Ah, okay. For all genius, would there be a one-to-one correspondent for all genius? I don't know. Yeah, I don't know. You want a full lecture on Anyon condensation? Yes. The question is, can we do that easily? No, I'm not sure I can do that before lunch. Now, how to build UMTC by condensing Anyon from other UMTCs? But that's another story. Maybe you will discuss that during your lecture. No, there is a way to do that, but it's not that simple, and I'm not sure I can reconstruct that just like that. Sorry. It's time for lunch.
Thanks, Julien.
Thank you.
It's around the time.